What is a linear transformation? Let us give a formal definition. A vector function that maps vectors of size n to vectors of size m is a linear transformation if for all vectors x and y of size n and all scalars alpha, transforming a scaled vector is the same as scaling a transformed vector. More formally, L of alpha times x equals alpha times L of x. And transforming the sum of two vectors is the same as summing the two transformed vectors. More formally, L of x plus y is equal to L of x plus L of y. We have already seen the example where a vector is rotated through an angle, and you practiced by reasoning about reflection. How does one prove whether a vector function is a linear transformation or not? Let's look at some examples. First, we look at a function that maps chi0 and chi1 to the vector with chi0 plus chi1 as its first component and chi0 as its second component. We will formally prove that this function is a linear transformation. To do so, we pick arbitrary scalar alpha and vectors x and y in 2D. By picking arbitrary scalar and vectors, whatever we conclude holds for all scalars alpha and vectors x and y. This is because there's nothing special about the alpha, x and y that we choose at this point. We now need to show that f of alpha times x is equal to alpha times f of x, and f of x plus y is equal to f of x plus f of y. First, let's look at scaling. Alpha of alpha times x equals f alpha times the vector chi0, chi1. Now, scaling a vector means scaling the components, which yields this. If we then apply the function, the result is this. Finally, we can factor an alpha out of the first component. The question is whether alpha times f of x equals the same expression. Let's start with alpha times f of x. This equals this, which equals this, and finally this equals that. If you compare these two, you see that they are the same. So, both f of alpha times x and alpha times f of x evaluate to the same expression. This means they are always equal. Mathematicians often like to show how clever they are, and would arrange this argument as follows. First, they would start with f of alpha times x and come up with the string of equalities that we just saw before. Then they would work with alpha times f of x, but on a piece of scrap paper. Once they figure out that this evaluates to the same expression, they would then write the sequence of equalities in reverse order as such. By then linking the two sequences of equalities, they would show that f of alpha x equals alpha times f of x. Okay, now we move on to f of x plus y and show it equals f of x plus f of y. We can again give sequence of equalities separately for f of x plus y and f of x plus f of y. Notice that they evaluate to the same expression if you recognize that scalar addition is commutative. We can then make this one continuous sequence of equalities as follows. We conclude that this vector function is a linear transformation. Let's look at how to show that a vector function is not a linear transformation. Here is the vector function that maps a vector of two components, which we will call chi and psi here, just to be different, to a vector with chi plus psi as the first component and chi plus 1 as the second component. Now, I happen to know that this is not a linear transformation. We will later see a systematic way of determining this. For now, we're just going to prove it. How do you show that something is not true? You give a counterexample. So, let's see if we can find an example where scaling a specific vector and then transforming it is not the same as first transforming the vector and then scaling it. Let's first try the scalar 1 and vector 1, 1. If we evaluate f of alpha times x, we get the result vector 2, 2. If we evaluate alpha times f of x, we again get the result vector 2, 2. Did we just get lucky, or is this always the case? Let's try a different choice. Let's pick alpha equals 0 and the vector x equal to 1, 1. Now, f of alpha x evaluates to the vector 0, 1. But alpha times f of x evaluates to the vector 0, 0. We have a contradiction. So, for this choice of alpha and x, it is the case that f of alpha x is not equal to alpha times f of x. Hence, the function is not a linear transformation. To summarize, linear transformations are special vector functions that have the property that one can scale first and then transform, or transform first and then scale, and one can add first and then transform, or transform first and then add. Some vector functions are linear transformations, others are not.